Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture, just for a second, the absolute most terrifying, most destructive force in the entire universe.
I'm pretty sure I know exactly where you're going with this.
Right, because if you ask anyone on the street to name the ultimate cosmic monster, most people are going to say the exact same thing without skipping a beat. A supermassive black hole.
Yeah, the classic space vacuum cleaner.
Exactly. We have this image so deeply ingrained in our collective consciousness, of these relentless, bottomless pits just sitting at the dark center of galaxies.
And the prevailing cultural idea is really that they are just the ultimate destroyers.
Yeah, they swallow ancient stars whole, they shred wayward planets into confetti, they even trap light itself in a gravitational prison.
It's basically the rule of the cosmos. If you get too close, that is it. Game over.
Right, you are spaghettified, pulled apart atom by atom, and permanently erased from existence.
And honestly, it's a reputation that it's certainly earned. From a purely mechanical standpoint, the event horizon...
That's the point of no return, right?
Mm-hmm. Exactly. The event horizon around a black hole is where physics, as we currently understand it, essentially just clocks out.
Wow. Just breaks down entirely.
Right. The gravity is so overwhelmingly intense that nothing, not even a massless photons of light, has the escape velocity required to leave. It's a literal tear in the fabric of space-time.
So it makes total sense why the cosmic destroyer narrative is the one that dominates.
Oh, absolutely. It is the ultimate one-way street in astrophysics.
But what if we have it all wrong? Or I guess, maybe more accurately, what if we are only looking at one side of the coin here?
Because there's always another side.
Exactly. I want to completely flip this assumption on its head today. What if these terrifying world-ending destroyers are actually the universe's most prolific creators?
That's the massive paradigm shift we are facing right now.
Right, because what if the very places we thought were the absolute worst, most hostile neighborhoods in the cosmos are actually the biggest, most active planet nurseries in existence?
It's wild, but we are truly on the verge of having to completely rethink our fundamental map of the cosmos.
Because for decades, whenever astronomers wanted to understand where planets come from, we really only looked at one specific thing.
Young stars. We viewed stars as the sole exclusive parents of planets.
Like that was the only recipe we thought existed.
Right. But if we shift our gaze away from those quiet, predictable, stellar neighborhoods and look directly into the extreme, chaotic environments around active galactic nuclei.
And those are the actively feeding supermassive black holes, right?
Correct. When we look there, we find conditions that might be churning out not just a handful of worlds, but literally millions of planets.
Millions. It completely changes our understanding of where life and new worlds can even exist.
It really does. It flips everything upside down.
I have to admit, when I first encountered this concept, my immediate thought was that it sounded like a typo in a physics paper.
A lot of people thought that at first.
Yeah, because we are going entirely off the traditional map today. We are going to start by looking at the actual anatomy of an active supermassive black hole.
Because it's not just a featureless void.
Right. As I've learned, it is not just a floating drain plug in space. There is actual architecture there.
Massive, complex architecture.
Exactly. Then we're going to travel to its outer edges where somehow fragile dust actually manages to defy total destruction.
Which is the key to everything.
Yeah. And then we will explore the insane speed and the sheer massive size of the planets forming in that environment.
And the sizes get truly ridiculous.
They really do. And finally, we are going to look at some bizarre, exotic worlds that literally blur the line between what we call a planet and what we call a star.
It is a phenomenal journey, and what I really appreciate about it is that it forces us to question our deep-seated assumptions.
About, what's required for creation.
Exactly. Human beings naturally associate creation with calm, stable, nurturing environments.
Right, like a warm incubator.
But the universe has a funny way of proving that extreme chaos can be just as generative, if not significantly more so.
All right, well, let's start with the monster itself. Supermassive black holes sit at the center of most large galaxies, including our own Milky Way, right?
Yes, almost all of them.
But the ones we are focusing on are what astronomers call active galactic nuclei, or AGNs.
Right, the active ones.
And my understanding is that these are the ones that are aggressively feeding. Like, they aren't just sitting there dormant.
No, they're actively pulling in massive amounts of surrounding gas, dust, and even whole stars.
And that feeding frenzy creates a phenomenal amount of activity.
It does. To understand the environment, we first have to discard the idea of a black hole as just a dark, quiet sphere.
Okay, so what does it actually look like?
Well, when a supermassive black hole is actively feeding, when it's an AGN, the material falling toward it doesn't just drop straight in.
Like water going down a drain?
Right, it's not a straight drop. Because everything in the galaxy has some amount of spin, that material actually spirals inward.
Okay, that makes sense.
And as it spirals closer to the event horizon, it gets compacted. It is moving at significant fractions the speed of light.
Which has to create an insane amount of friction.
Unimaginable friction. The particles are just colliding relentlessly. And this friction generates heat, temperatures in the millions of degrees.
Millions of degrees, wow.
Yeah, the material actually transforms into a glowing, superheated plasma, forming what we call an accretion disk.
Okay, so the black hole is essentially surrounded by a blindingly bright, incredibly hot whirlpool of plasma.
Exactly.
And this isn't a subtle phenomenon, right? The energy being released is just staggering. I was reading about the jets that get launched from these things.
Jets are incredible.
Yeah, because some of this material doesn't actually make it into the black hole. Instead, it gets channeled toward the magnetic poles and blasted out into space.
As incredibly high-energy jets, yes.
Yeah. And the scale of these jets is so difficult to wrap my head around. The baseline measurement is that at their base, right near the black hole, these jets can be as small as a few light hours across.
Right, and let's pause there to actually contextualize that, because light hours is a term astronomers throw around that can obscure the actual physical reality.
Yeah, let's do the math on that. Light travels at about 186,000 miles per second.
Which is fast.
Extremely fast. In 1 minute, that's roughly 11 million miles. In 1 hour, light covers over 670 million miles.
That's a huge distance.
So if the base of this jet is a few light hours across, we are talking about a column of highly energized particles that is roughly the width of our entire solar system out to maybe Jupiter or Saturn.
At least.
Which sounds incomprehensibly massive to a human being, but on a cosmic scale?
It's basically a pinhole.
Exactly, a tiny pinhole.
Well, I wouldn't call it a pinhole, but relatively speaking, it is incredibly narrow and focused at the source.
How does it stay so focused?
Well, the intense twisting magnetic fields around the black hole act almost like a cosmic rifle barrel. They constrict and accelerate this plasma.
So you have this beam, the width of our solar system, blasting outward at nearly the speed of light.
Right. But the true scale isn't the width. It is the length.
Okay, how long are we talking?
These jets stretch outward, cutting entirely through the host galaxy and deep out into the empty intergalactic space for hundreds of thousands of light years.
See, that is the part that breaks my brain. Hundreds of thousands of light years?
It's hard to visualize.
Because the entire Milky Way galaxy, from one edge all the way to the other, containing hundreds of billions of stars, is only about 100,000 light years across.
That's our whole neighborhood, yeah.
So you are telling me these jets from a single supermassive black hole can be several times longer than our entire galaxy?
That is absolutely correct. They are among the largest single structures in the universe.
That's just wild.
And it's not just these narrow piercing jets either. The intense energy from the inner accretion disk of the AGN also produces these broad, wispy, incredibly powerful radiation winds.
Radiation winds. That sounds intense.
Very. These winds sweep outward in all directions and are so forceful that they literally carve out massive bubble-like cavities in the surrounding cosmic gas.
Like blowing bubbles in water.
Yeah, but on a galactic scale, they are essentially acting like galactic bulldozers pushing matter out of the way.
Just clearing house.
Exactly. They can even shut down star formation in certain areas and actively shape the structural evolution of the galaxy itself.
Okay, let's unpack this for a second, because here is where I hit a massive logical roadblock.
Okay, what's the roadblock?
If I am trying to build a delicate, fragile thing like a baby planet, I need peace and quiet.
Sure.
But you have just described an environment where jets are shooting out for hundreds of thousands of light years and colossal radiation winds are blowing massive structural bubbles in the cosmic gas.
It's a violent neighborhood.
Yeah. How could anything possibly survive there? You have extreme X-ray radiation, high-energy particle jets, and hurricane-force galactic winds.
It sounds impossible.
It really does. If I'm listening to this, it honestly sounds like trying to build a delicate house of cards inside a Category 5 hurricane.
It does sound completely counterintuitive.
Yeah.
And historically, that is exactly why astronomers never bothered to look for planets in these regions.
Because why would you?
Right. We assumed it was physically impossible. But this is where we have to look much closer at the spatial anatomy of the environment.
Okay, so what are we missing?
The mistake is visualizing the black hole as a single point of absolute destruction that just radiates pure chaos equally in all directions forever.
Like a bomb going off constantly.
Exactly, but that isn't how the physics work. It has a vast, highly structured anatomy.
Structured how?
Well, the destruction, the extreme spaghettification from tidal forces, the intense X-ray radiation that strips electrons from atoms.
All the scary stuff.
Right, that all happens very close to the center. That is the realm of the event horizon and the inner accretion disk.
Okay.
But space is big. As we move outward radially from that central point, the physics begin to drastically change.
So if I'm understanding you, proximity is everything here.
Everything.
The danger isn't absolute everywhere. It is dependent on exactly where you are standing relative to the center.
Precisely. The environment is chaotic, yes, but it is a structured chaos with distinct boundary lines.
Like different weather zones on Earth.
That's a great way to put it. There are specific transition zones within this immense system. If you go far enough out from the center, the radiation actually drops by orders of magnitude.
Oh, really?
Yeah. The ambient temperature cools down just enough, and the dynamics of the swirling material fundamentally change.
So it calms down.
Relatively speaking, yes. We eventually leave the zone of pure destruction and enter the specific critical zones where creation suddenly becomes mathematically and physically possible.
And that brings us to the core conflict between the conventional wisdom of astronomy and what is actually happening in these outer zones.
The paradigm shift.
Exactly. Because normally, when we talk about planets forming, we aren't talking about black holes at all. We talk about young stars.
Right, the traditional model.
We have this very standard, comforting model of planet formation that we teach in middle school. A young star is born, and it has this leftover disk of gas and dust spinning around it.
Yes.
And over millions of years, that dust gently clumps together into pebbles. The pebbles stick together into boulders. The boulders crash into each other to form planetesimals. And eventually, after a lot of patience, you get a planet.
And astronomers call those protoplanetary disks.
Right.
And we call them that because historically, that is the gold standard for planetary science.
It's the only way we thought it worked.
Exactly. It is a highly complex process, but it relies heavily on that spinning disk of gas and dust, providing a relatively stable incubator.
And we know this happens, right? Like, we've observed these disks around countless young stars in our own galaxy.
Oh, absolutely. We've even reached a point technologically where we can take direct pictures of them.
Yeah, using advanced radio telescopes like LMA in Chile, right?
Yes, LMA has been revolutionary for this. We can actually look at these disks and see the dark, empty rings in the dust.
And those rings are where young, unseen planets are acting like cosmic vacuum cleaners, right? Just swooping up material as they orbit.
Precisely. So we know the stellar model works.
But here's the big reveal that completely upends the table.
This is the crazy part.
Giant versions of these exact same spinning disks of gas and dust also exist around supermassive black holes at the center of active galaxies.
Yes. Giant is an understatement. And if we connect this to the broader implications of astrophysics, it represents a massive shift in cosmic geography.
How so?
Well, what we are doing is taking the exact same mechanical structure.
Which is a central gravitational anchor surrounded by a spinning disk.
Exactly, and scaling it up to an almost incomprehensible degree.
It's deeply ironic to me, honestly. We've spent decades and billions of dollars building incredibly sensitive space telescopes specifically designed to stare at young, quiet stars.
Looking for Earth 2.0.
Right. We operated under the strict assumption that a stellar neighborhood is the only place in the universe that has the right recipe, the right temperature, and the right gravitational balance for baking a planet.
It was our only frame of reference.
We were basically standing on a street corner, obsessively looking at the local artisan bakery, completely ignoring the massive industrial-scale manufacturing plant operating just down the road.
I love that analogy, though. I would actually push back just a little on the word factory or manufacturing plant.
Oh, why is that?
Because that implies a level of controlled intentional design.
Fair point.
What we're talking about here is more akin to an avalanche that, purely by the laws of physics, happens to perfectly assemble a billion snow castles on its way down the mountain.
Wow. Okay, yeah, that is a very different mental image.
The chaos itself is the mechanism. But your point stands regarding our observational bias. It highlights a very common pitfall in science. We look for what we know.
We're biased toward our own existence.
Exactly. Because human beings live on a rocky planet orbiting a very average, middle-aged, yellow dwarf star, we naturally assumed that stars are the mandatory prerequisite for planetary formation.
It's the classic, looking for your lost keys only under the streetlight because the light is better there.
That's exactly what it is. But physics is completely blind to our biases.
Right.
The mechanics of planet formation, the simple act of solid dust grains colliding, sticking together via electrostatic forces, and eventually clumping enough to generate their own gravity.
That might just be universal.
Entirely universal. It appears to scale up seamlessly from the relatively tiny environment of a single stellar neighborhood to the massive galactic-scale environment of a supermassive black hole.
So the physics don't care about the source of the gravity?
Not at all. The fundamental physics of clumping dust do not care if the gravity well in the center belongs to a star or a black hole. They only care if the local conditions in the disk allow for the process to happen.
But that brings me right back to the environment. Even if there is a massive disk, we know the inner part of that disk, that accretion disk you mentioned, is an absolute inferno of plasma and X-rays.
Yes, it is.
So exactly where in this giant, violent, supermassive structure could you possibly find the right conditions to bake a planet without the ingredients getting instantly vaporized?
And that leads us to the very outer edges of these black hole disk structures. Astronomers call this specific outer region the torus.
The torus. Geometrically speaking, that's just a fancy word for a giant donut shape, right?
Correct. Imagine a massive, thick, donut-shaped ring of dust and cold gas that completely surrounds the inner accretion disk at a significant distance.
Okay, I'm picturing it.
While the inner disk is flat and razor-thin because of the extreme speeds in gravity, the torus is puffed up and thick due to turbulent dynamics and radiation pressure pushing outward. Okay. And here is the crucial discovery that really anchors this whole theory. In these outer tori, the temperatures and the physical conditions are incredibly similar to those found in the planet-forming disks around ordinary young stars.
Wait, really? It's like finding a perfectly calm, climate-controlled greenhouse operating on the outer rim of an actively erupting volcano.
That's one way to look at it, sure.
You have this absolute chaotic inferno in the center, but out on the very edge, shielded by the sheer volume of material between it and the center, the temperature suddenly drops to a manageable level.
I think the volcano analogy is maybe a bit too serene, though.
Oh, really?
Yeah, it's more like trying to understand radiation shielding.
Okay, explain that.
So the inner disk is blasting out lethal X-rays, right?
Right.
But gas and dust are exceptionally good at absorbing radiation. We call this optical depth.
Optical depth, okay.
As the X-rays try to push outward from the black hole, they hit a wall of gas. That gas absorbs the extreme energy, heats up, and re-radiates it as lower energy infrared light.
So it steps it down.
Exactly. Then that infrared light hits the next layer of gas, gets absorbed, and re-radiated again.
Oh, wow.
By the time that energy propagates all the way out to the torus, it has been stepped down so many times that it is no longer a destructive death ray. It's just a warm glow.
That makes perfect sense. Distance and optical depth are the keys to survival here.
Yes.
So the inner material is essentially throwing itself on the grenade to protect the outer material.
In a sense, yes. That's a good way to picture it. In the torus, the intense heat and the extreme radiation from the black hole's feeding frenzy have dissipated just enough. We cross a very specific boundary called the sublimation radius.
Sublimation radius? Break that down for me. Sublimation is when a solid turns directly into a gas, like dry ice, right?
Precisely. If a grain of dust wanders inside the sublimation radius, it gets too close to the black hole's heat.
And boom.
Well, not boom, but the temperature exceeds the melting point of rock and metal, and the solid dust grain instantly vaporizes into free-floating atoms. It is destroyed.
But just outside that boundary.
Just outside that boundary, out in the torus, the temperature drops below that critical threshold. Out there, solid matter, actual grains of silicate dust and ice, can persist without boiling away.
And dust is the magic ingredient, right? Without solid dust grains, you can't build a rocky planet.
Right.
You can't build the core of a gas giant. You just have a cloud of hot gas.
Exactly. Dust is the absolute prerequisite for planetary architecture. Planet formation is, at its core, a game of deep patience and survival.
You need time.
Lots of time. You need tiny microscopic particles of dust to gently collide and stick together.
At first, it's just static electricity holding them together, right? Like dust bunnies accumulating under a couch.
Great analogy, yes. Then they grow a little bigger into pebbles and a little bigger into boulders until they finally have enough mass for their own gravity to take over the construction process.
And this process takes millions of years of undisturbed time.
Yes, it does. The simple fact that dust can physically survive in the torus without being annihilated means that the fundamental clock of planet formation can actually start ticking in this environment.
Okay, so if the recipe exists in this outer donut, this torus, and the ingredients aren't getting vaporized, just how many planets are we actually talking about here?
That is the big question.
Because a normal star, like our sun, gives us roughly 8 planets, maybe some dwarf planets like Pluto, some moons, an asteroid belt. It's a nice, manageable family.
Right.
But we are talking about a disk around a supermassive black hole. The sheer volume of material must be completely off the charts compared to our little solar system.
This is where the theoretical models start yielding numbers that frankly sound like science fiction.
Oh, I'm ready for this.
But they are rooted entirely in rigorous math.
Mm-hmm.
Researchers, including a prominent team led by Barry McCurran from the City University of New York, wanted to actually quantify this. They didn't just want to say, hey, it's theoretically possible. They wanted to know what the demographics of this environment would actually look like.
So what did they do?
So they took everything we know, data on the temperatures, the gas densities, the mass of the black holes, and they fed it into a highly complex computer model of a magnetized black hole disk.
Let me stop you there, because computer model can mean a lot of things.
True.
When I hear computer model, I usually think of meteorologists running hurricane simulations. You know, they plug in current wind speeds, ocean surface temperatures, barometric pressure, and the computer runs the physics forward to predict where the storm will hit.
Right.
Are these astrophysicists doing the exact same thing here, just swapping out barometric pressure for gravitational pull and radiation intensity?
That is an excellent analogy.
Yeah.
Yes, they're building a mathematical sandbox. They define the rules of physics, gravity, thermodynamics, fluid dynamics, and then they set the initial conditions based on what we actually observe in active galactic nuclei.
Like the density of the gas and stuff.
Exactly. They establish the gas density, the size of the dust grains, the temperature gradients, but the key phrase you noted earlier was magnetized black hole disk.
Yeah, why does that matter?
This isn't just about gravity. Plasma in an accretion disk generates intense, twisting magnetic fields.
And why do magnetic fields matter so much for building a planet?
Because of something called the magnetorotational instability, or MRI.
MRI, like at a hospital.
Same acronym, very different physics. In a perfectly smooth, frictionless disk of gas, dust would just orbit forever and never clump together. You need friction. You need turbulence.
Ah, I see.
The magnetic fields threading through the plasma create this immense turbulence. They act almost like sticky threads, creating drag.
Ah, okay.
This drag slows down the gas, forcing it to spiral inward. But crucially, this turbulence creates swirling eddies and pockets of high density where dust gets trapped. It forces the dust grains to collide more frequently.
It's like stirring a cup of tea. If you just let it sit, the sugar stays at the bottom.
Yeah.
If you stir it, you create turbulence that forces everything to mix and interact.
Exactly. So the McKernan team's computer models simulate this specific physics over millions of years of accelerated virtual time.
And what did they find?
They calculated the collision rate of the dust, how fast it actually clumps together in that turbulent magnetic environment. They modeled the final potential size of the planets, and they looked at the accretion rate, meaning how much extra surrounding dust and gas these newborn rocky cores would swallow up as they orbited through this incredibly dense torus.
And the results? This is the part that completely shatters my mental model of the galaxy.
It's pretty shocking.
Yeah, because the approximate model suggests that these AGN dust torus might host the largest populations of planets in the entire universe.
By far.
We aren't talking about 8 planets. We aren't talking about 100. We are talking about tens of millions of planets forming in a single environment around a single black hole.
Tens of millions.
Yeah.
Forming concurrently in the dark.
It's just staggering to think about.
If you just calculate the raw volume of a torus around a supermassive black hole, It contains vastly more building material than a standard star's protoplanetary disk.
Right.
It's the difference between the amount of water in a backyard swimming pool and the amount of water in the Pacific Ocean.
Wow.
And because the dynamics of that magnetized disk actively accelerate the clumping process through turbulence, it forces us to entirely reconsider our galactic census.
I always pictured the galaxy as this dark, empty ocean with these little isolated islands of stars.
It's the standard view, yeah.
And each glowing island has a few tiny pebbles, planets circling it. We thought all the real estate was on the islands.
Yeah.
But this model suggests the dark, terrifying whirlpool at the center of the ocean is actually a massive swirling continent packed with millions of unseen worlds.
And that completely flips the script on what is actually normal in astrophysics.
How so?
We have always inherently assumed that the normal planets, the ones orbiting stars like Earth orbits the sun, were the standard template for planetary existence.
Right, because that's what we are.
Exactly. But if a single AGN torus can produce tens of millions of planets, while a star only produces a handful, simple math dictates that stellar planets might actually be the minority in the universe.
Wait, really? The minority?
Yes. The vast, overwhelming majority of planets might not experience sunrises or stellar days at all. They might be orbiting in eternal twilight, swirling around supermassive black holes.
So if I'm a researcher looking at this data, I'm not just seeing a lot of planets. I'm seeing planets that form on a completely different timeline. The CUNY data shows that these planets grow much, much faster than planets born around normal stars, right?
Yes, the temporal scale is drastically compressed.
Why is that?
And that rapid growth is directly tied to the mechanism of accretion in an environment characterized by high density and high gravity.
Okay, elaborate on that.
The intense gravity from the distant black hole doesn't just hold the torus in place. It continually pulls new material in, keeping the torus incredibly dense and packed with material.
So it's always full.
Right. A young planet in this environment is essentially born into a high-pressure, all-you-can-eat buffet that never runs out of food.
Oh, wait, let's address the massive elephant in the room here.
Okay, what's that?
If you're listening to this and wondering how a planet doesn't just get sucked in instantly or crushed, you have to remember how orbital mechanics work.
Right.
We know that if a moon or a planet gets too close to a massive gravity well, whether it's a star or a black hole, tidal forces can rip it apart. It's what happened to form Saturn's wings, just on a smaller scale.
Exactly.
So if the gravity is so intense that it's compressing the entire disk, how does that intense gravity actually help a planet grow rather than just shearing it into dust?
It is a brilliant question, and it comes down to a delicate balance defined by something called the Roche limit and a concept known as the Hill sphere.
Let's define those because they sound crucial.
They are. The Roche limit is the minimum distance a smaller celestial body can be from a massive body before the tidal forces overcome the smaller body's own internal gravity, tearing it apart.
So it's a safety line.
Exactly. If the planet were too close to the black hole, inside the Roche limit, the gravitational pull on the near side of the planet would be so much exponentially stronger than the pull on the far side that the planet would just physically disintegrate.
It would be stretched and shredded.
Right. That's the spaghettification we always hear about.
Okay.
But out in the torus, the planet is far beyond the Roche limit. The tidal shear from the black hole is significantly weaker out there.
That makes sense.
However, the planet still possesses its own gravity. The region around the planet where its own gravity dominates over the gravitational pull of the central black hole is called its Hill sphere.
Wait, what's a Hill sphere again?
It's essentially the planet's gravitational territory. Anything that wanders into the planet's Hill sphere belongs to the planet.
Okay, so the black hole is dictating the massive traffic patterns of the entire donut, but the planet has its own local gravitational jurisdiction.
Precisely. And because the material in the torus is so dense, there is an enormous amount of mass constantly flowing through the planet's Hill sphere.
Ah, I see where this is going.
In a standard, sparse disk around a young star, a growing planet eventually clears its orbit. It acts like a snowplow, sweeping up all the available dust and gas in its path.
And then what?
Once the path is clear, its growth dramatically slows down because there's simply nothing left nearby to eat. It has reached its final mass.
It essentially starves itself by being too efficient at eating.
Right. But in the Aegean torus, the buffet is continuously restocked.
Because the black hole keeps pulling stuff in.
Exactly. The violent swirling dynamics of the supermassive disk mean that fresh gas and dust are constantly being pushed into the planet's orbital path. The young planet just keeps eating.
Wow.
It never clears its orbit because the orbit is constantly refilling.
And because it never has to stop eating, the scale of these worlds becomes mind-blowing. We aren't talking about billions of Earth clones here.
Not at all.
The models show that these worlds easily grow far larger than our planet. We are talking about rocky cores that just keep packing on mass, eventually sweeping up enough dense gas to balloon into something that completely dwarfs Jupiter.
Yes. They are supersized giant planets living their entire existence in the absolute fast lane of cosmic evolution.
Which naturally forces an astrophysicist to ask the next logical question. If a planet is sitting at an endless buffet, and the physics of the environment allow it to continuously gorge itself without ever running out of raw material, what happens when it doesn't stop growing?
That is the multi-million-dollar question.
Is there a hard physical limit to how big a planet can get before the laws of physics intervene and it stops being a planet altogether?
And this is exactly what blows my mind about the McKernan team's research. Because the rigid line we draw between what is a planet and what is a star starts to completely blur here.
Yeah, the core information from these models reveals that some of these newly formed giant worlds in the Aegean Tauri can accrete so much gas and dust that they actually cross the mass threshold and ignite into new stars.
It is a profound, almost philosophical shift in how we categorize celestial bodies.
It's unbelievable.
The formal scientific definition in the literature notes that this vigorous, unceasing accretion leads to objects with stellar masses. The researchers actually define this as a completely new, mathematically proven core accretion channel for star formation.
It's absolutely wild. Think about it like packing a suitcase for a trip.
Okay.
In a normal stellar system, you eventually run out of clothes to pack. The suitcase is full, you zip it up, and that's your planet.
Right. The orbit is cleared.
But in this environment, you have an infinite closet. You just keep throwing clothes in, keep sitting on the suitcase to compress it, throwing more clothes in, sitting on it again.
I see where this analogy is going.
Eventually, the sheer mechanical pressure inside that suitcase becomes so unbelievably intense that the zippers fuse together on a molecular level, and the whole thing bursts into flames.
Well, your analogies are getting more violent, but mechanically, you are describing the thermodynamics of core ignition perfectly.
Thank you.
To truly appreciate how radical this core accretion channel is, we had to contrast it with the traditional, universally accepted model of star formation.
Okay, let's do that.
Usually we think of stars forming from what we call the top down.
Right, a giant nebula, a big cloud of gas out in space.
Yes, you have a massive, diffuse, incredibly cold cloud of molecular gas. It sits there for eons.
Just floating.
Right. Something triggers a collapse, maybe a shock wave from a nearby supernova or a gravitational perturbation. A section of that massive cloud begins to fall inward under its own crushing weight.
Okay.
As it collapses, it gets denser and hotter. This is driven by gravity pulling the gas together. Eventually, the core of this collapsing cloud becomes so compressed and so hot that the individual hydrogen atoms are literally forced to overcome their natural repulsion and fuse together into helium.
And that's fusion.
Exactly. That nuclear fusion releases an enormous amount of outward energy, balancing the inward pull of gravity, and a star is born, top down. A big, loose cloud collapsing into a dense, bright star.
But the mechanism we are talking about in the black hole torus, this is bottom-up star formation.
Exactly. It flips the entire sequence in reverse.
Because it starts as a planet.
Right. You start with a microscopic sub-millimeter piece of solid silicate dust. Through random electrostatic collisions, it clumps into a pebble. The pebble grows into a rock. The rock grows into a massive planetary core.
Just building blocks.
Because the core has so much gravity, it starts pulling in thick envelopes of surrounding gas. It becomes a gas giant, much like Jupiter.
Which is where the process normally stops in a quiet, stellar neighborhood.
Right. Jupiter didn't have enough surrounding gas to keep growing. But because this particular gas giant is orbiting inside the Aegean Taurus, the buffet never closes.
They just keep eating.
It keeps pulling in gas, packing on mass, getting heavier and heavier. Eventually, the immense weight of all that accreted gas creates such extreme pressure and temperature at the very center of the planet that it forces its own internal atoms to fuse. It doesn't collapse from a cloud. It builds up from a seed. It transitions from a planet to a star, entirely from the bottom up.
So you literally have stars being born out of the ashes of supersized planets, completely rewriting the fundamental boundaries of planetary and stellar evolution.
It really does pose a massive categorical problem.
Yeah. If I somehow manage to point a telescope at one of these objects when it's exactly halfway through this process...
The awkward teenage phase.
Exactly. When it's too massive to be a normal gas giant but hasn't fully ignited nuclear fusion yet, what do I call it? Is it an incredibly bloated, massive planet? Or is it a failing, unignited star?
At that point, it becomes a purely semantic argument.
Really?
Yeah, we as humans have an innate desire to categorize things based on our local observations. We want neat little boxes. This is a planet, this is a brown dwarf, this is a star.
Right, we like labels.
But the universe doesn't care about our taxonomy. These models show us a continuous evolutionary spectrum where a single grain of dust can theoretically evolve into a raging nuclear furnace, provided it exists in the right environment and is fed enough material.
And as if bottom-up star formation wasn't weird enough, the models predict something even stranger.
Oh, yes.
If you look closely at the math, they predict the possible formation of exotic, massive objects made mostly from dust.
Yes, the dust giants.
If the bottom-up stars challenge our definitions, these dust giants challenge our basic understanding of structural physics.
They do. This is perhaps the most alien concept to emerge from the data. These objects would be fundamentally unlike absolutely anything known in the planetary systems around ordinary stars.
So what exactly is a massive object made mostly of dust? I am trying to visualize the physical structure of this for anyone listening.
It's tricky to picture.
Because we know gas giants like Jupiter and Saturn, they have massive swirling hydrogen atmospheres over relatively small, dense cores. And we know rocky worlds like Earth, Venus, and Mars, solid metal and silicate rock crusts with very thin atmospheres.
Yes.
But a giant ball of mostly dust. I can't even get the dust bunnies under my couch to hold their shape when I sweep them up. How does a massive planet made of dust even structurally hold together?
To understand how these exotic dust giants could possibly form and maintain their structure, we have to once again contrast the AGN environment with standard stellar systems.
Okay, let's do the comparison.
In a normal system, when the young star finally ignites nuclear fusion at its core, it produces a very powerful outflow of particles called a stellar wind.
And this acts like a giant cosmic leaf blower.
That is the exact perfect analogy. The stellar wind turns on and physically sweeps the remaining loose, unconsolidated gas out of the entire planetary system.
So the buffet is forcefully cleared.
Exactly. What you are left with are the dense, rocky cores that were strong enough to resist the wind, our terrestrial planets, or the gas giants that managed to lock in their thick atmospheres with immense gravity before the loose gas was blown away.
So the stellar leaf blower removes the construction material, leaving only the finished products.
Precisely. But in the extreme, hyperdense environment of the AGN torus, the dynamics are entirely different.
Because there is no leaf blower.
Right. There's no stellar leaf blower clearing the immediate area. The torus is continuously replenished and dynamically stirred by the overarching gravity of the supermassive black hole.
So the dust just stays there.
Yes. Furthermore, the sheer volume and density of solid dust particles in certain specific bands of the torus are extraordinarily high.
How high are we talking?
So high, in fact, that when a planetary body begins to accrete mass, it isn't just sucking in a gentle stream of gas. It is aggressively sweeping up massive over quantities of solid dust faster than it can sweep up gas.
So instead of a standard rocky core slowly gathering a giant gaseous envelope of hydrogen, you have a rocky core gathering a giant thick envelope of solid dust.
In a way, yes. But it wouldn't be like flying a spaceship into a loose, powdery cloud.
Oh, it wouldn't.
No. The sheer gravitational pressure of an object that massive would compact this dust to an incredible degree. Gravity would force it into a massive, structurally bizarre, semi-solid state.
Wow.
We are talking about celestial objects that might have the total mass of a giant planet like Jupiter, but instead of being made of light gas, they're composed almost entirely of compacted silica grains, heavy metals, and complex carbonaceous material.
So if I were to somehow dive into one of these exotic dust giants, assuming my ship wasn't instantly crushed by the immense gravity, what would the geology actually be like?
It's a fascinating question.
Because it wouldn't have a standard, distinct molten iron core and a clear, solid, rocky mantle like Earth has, right?
It is entirely theoretical, of course, because we have never observed one directly. But it is highly likely you wouldn't find the neat geological differentiation we see on Earth.
Why not?
Well, on our planet, when it was young and molten, the heavy iron sank to the center to form the core, and the lighter silicates floated up to form the mantle and crust.
Right, that makes sense.
But depending on exactly how rapidly these dust giants form in the torus, The immense sudden pressure might prevent that settling. The material might remain somewhat uniformly mixed, a massive homogeneous blend of rock and metal.
That sounds incredibly strange.
Or, conversely, it might stratify in entirely novel, bizarre ways based purely on the extreme pressure physics we can hardly replicate in the lab.
It just goes to show how much is still out there.
It deeply reflects how little we truly know about the universe, given that whole new categories of celestial bodies, things we don't even have proper names or classifications for yet, are almost certainly hiding right now in these dark corners of the cosmos.
It's absolutely wild to think about. We are essentially mapping out a completely invisible ecosystem.
Exactly.
We are relying on the immutable laws of physics and incredibly complex mathematics to confidently prove that these bizarre leviathans have to exist out there in the dark, even if we can't take a picture of them yet.
And that is the true beauty of theoretical astrophysics.
It really is.
We use the fundamental laws of physics that we test, verify, and rely on locally, gravity, fluid dynamics, thermodynamics, and we confidently apply them to extreme distant environments to see what the math predicts.
We aren't just guessing.
No, we are calculating. In this case, the math strictly predicts a hidden zoo of exotic objects that fundamentally challenge our baseline understanding of planetary science.
Okay, I feel like we need to take a collective breath and recap this wild ride because we have covered a massive amount of dense conceptual ground today.
We really have.
We started by looking at supermassive black holes, which we have always known as the ultimate cosmic destroyers. We pictured their jets shooting energized plasma hundreds of thousands of light years across intergalactic space, and their radiation lines ruthlessly blowing massive cavities in the cosmic gas.
The ultimate hostile environment where survival seemed scientifically impossible.
Exactly. But then we looked closer. We pushed past the assumptions, and we found that on the very outer edges of their massive accretion disks, far away from the lethal X-rays, there are these giant donut-shaped rings called tori.
And miraculously, physics dictates that these tories act as vast, shielded safe havens.
Right. The conditions there, thanks to the optical depth of the gas absorbing the radiation, are just right for fragile dust to survive.
The hidden Goldilocks zone of a supermassive black hole, where the temperature drops just enough to allow solid matter to persist and begin the long, slow dance of clumping together.
And because that solid matter persists, and because the magnetic turbulence constantly stirs the pot, these dark environments might actually manufacture the largest populations of planets in the entire universe.
The numbers are just astounding.
We are talking tens of millions of planets per black hole, effectively turning our understanding of the galactic map completely upside down.
It really does.
We learned that the dense, never-ending buffet of material creates Jupiter-dwarfing giants, bizarre, exotic dust worlds that defy conventional geology, and even planets that grow so relentlessly massive from the bottom up that they literally ignite their own cores into stars.
Completely rewriting the textbook rules of how stars are born.
It is a breathtaking synthesis of ideas.
It is. But as an astrophysicist, I do want to ground the conversation just a bit before we finish.
Oh, okay. Let's ground it.
It is crucial to remember the scientific method here. While the computer models, the fluid dynamics calculations, and the brilliant insights from teams like the researchers at the City University of New York are mathematically rigorous and highly compelling.
We still have to prove it.
Exactly. We are currently operating at the bleeding edge of the theoretical frontier. This research gives astronomers plenty of substantial food for thought, but the universe ultimately demands empirical proof.
So we need to actually see them.
Yes. It will require future, undeniable observational evidence to definitively prove that these millions of planets are out there. We will need next-generation telescopes, perhaps advanced infrared arrays or novel gravitational wave detectors, and incredibly clever observational techniques.
Because looking into a dust donut around a black hole is probably pretty hard.
Extremely hard. We have to peer through that thick, dusty torus and catch the faint, telltale signature of a planet in the actual act of forming around an active galactic nucleus.
It's the ultimate cosmic game of hide and seek, played on a galactic scale.
Precisely. The math explicitly says they are there. The physics not only allow for it, but actively encourage it. But observational astronomy demands that we see it. That is the next great, exciting challenge for the astronomical community over the coming decades.
So what does this all mean for us, sitting down here on our little rocky world, orbiting a very average, quiet, middle-aged star? I want to leave you with a final thought to mull over.
Okay, let's hear it.
The next time you step outside on a clear night and look up at the sky, It's so easy to just look at the twinkling stars and imagine the tiny, isolated planets orbiting them. That's what we've always been taught to do. We look at the light.
It's human nature.
But next time, I want you to look into the dark spaces between the stars. Look past the constellations toward the invisible, supermassive center of our own Milky Way galaxy.
The dark spaces hold so much more than we think.
And instead of picturing a terrifying, empty void of pure destruction, I want you to imagine tens of millions of massive, exotic worlds, dust giants and bottom-up stars, thriving unseen in the dark, swirling in a massive cosmic dance around the biggest monsters in the universe.
It's a universe where creation doesn't just happen in the warm light of a sun, but in the deepest, most turbulent magnetic shadows.
Exactly. It makes you wonder what else physics is hiding from us in the dark.